So please sir, come and start here. Thank you.
So good morning to all. I Dr. Ravi. I am thankful to NRI College, Principal Sir, Dean Ma'am, and also VIP for giving this opportunity to me. And thank you all, participants also. So today we will discuss about MEMS devices and based on semiconductor. So we will first start with how we have to think about devices, then we will come to design part. After that, how we have to make it design to fabrication, then we will discuss how to design a mask for that particular device, and then how to optimize this device for a particular application. We have so many applications in MEMS. We can even go for sensing purpose, sensing in medical sensing, in biological sensing, physical sensing. Then we can utilize same device for the purpose of communication purpose. So how we have to complete all these. So may I know how many of you are PhD? So that's why I can align with you. And okay. And how many of you MTech? All of them. All of them. Good. That is very good. You have to have interaction, fruitful interaction with me so that we can benefit from this. And whatever you have doubt, because this will help you to teach IC technology and whatever VLSI subjects. Clear? It will give you a very beautiful concept towards your understanding towards MEMS fabrication, because it is somewhat aligned with our VLSI fabrication, because both are something different. In MEMS, what is difference and VLSI? VLSI will have a simple same fabrication step we have to use for all kind of devices. Clear? But in MEMS, fabrication is entirely different. It's changing according to device. But in VLSI, it is not changing according to device, because we are using PDK in the VLSI to fabricate the device. But here we have to go through MEMS fabrication step. Okay? So we will start. This is my presentation outline. So we will start first with acoustic wave devices. So what are these devices basically? These devices basically work on the principle of inverse piezoelectric effect. Okay. So what is basically piezoelectric effect? So for example, if any material is subjected to, piezoelectric material is subjected to force or stress or pressure, then what will happen? These molecules will be polarized, and due to this, electric charge will be generated. So it means basically it will convert the mechanical energy into electrical energy with the help of piezoelectric effect. But this device is working on the principle of inverse piezoelectric effect. So what is the inverse piezoelectric effect? Basically, once we apply a voltage to a device, then what will happen? Due to this stress will be generated into the piezoelectric layer, and due to this stress there is a mechanical vibration into the device, and due to this mechanical vibration it will resonate at a particular frequency. So this frequency depending on our piezoelectric layer. So we will see how it will be calculated resonant frequency for this device. So acoustic wave devices can be excited by a various means. It may be mechanical impact, pulse, thermal energy, or based on inverse piezoelectric effect. So we have basically two types of piezoelectric devices. One is the surface acoustic wave, and another one is the bulk acoustic wave. So this is the first type of device, that is the surface acoustic wave device. So what we have in this device we have a piezoelectric substrate. Okay. So in this piezoelectric substrate, first we have to pattern my IDT electrode. So this side and this side we have an IDT electrode. For this we have to generate the acoustic signal, and between this input IDT and output IDT we have a delay line. So this delay line is used for our sensing area, wherever we have to develop our sensing layer to sense anything. Clear? So once we apply any voltage to this input electrode, then due to this what inverse piezoelectric effect will happen. Stress is generated, and due to this stress, it will generate a particular resonant mode. And this resonant mode is depending on this piece size. Whatever is this piece size, this size is, if this size is very small, our frequency is high. Clear? So this space, spacing between these two identity decide my resonant frequency in the short device. Clear? Then once you have a acoustic signal generated, it will travel through this delay line. So in this delay line, we have a sensing layer. So what is the role of this sensing layer? Once this signal will comes into delay line, it will perturbate by the environment. Means for example, we evaporate a particular gas, then it will absorb to this particular sensing layer. So before any exposure of gas, what we have another characteristic of our acoustic signal. But once we have the acoustic signal changes due to the evaporation of gas, that will be measured at the output identity. So that's how what we have basically in this acoustic devices. We have a change in the frequency based on the change in the sensing layer environment. Clear? So basically we have here measured the change in the frequency with the help of participation of any kind of gases or physical quantity, pressure, it may be anything. Clear? Then next we have a bulk acoustic devices. So what we have in this bulk acoustic devices, instead of identity we have a piezoelectric substrate, and bottom side and top side we have a electrode. Okay. So what is here basically, once we apply a signal between bottom and top electrode, due to this stress will generate, and due to this stress there is a mechanical vibration and our resonant mode will be generated. And this resonant frequency will be depending on the thickness of the piezoelectric substrate. So in this quartz crystal micrograins, what we have a problem? We have a problem that we can't go beyond a particular frequency because this substrate thickness, because this is depending on the substrate thickness, and we can't handle a very thin substrate. So we can go up to 10 megahertz with the help of that. But if we want to go for PPT level detection, and if you want to design filter for a high frequency, so we can't go with this QCM based sensor. So what we have, okay. So what we have here is this thickness, we can't go beyond a particular thickness because it's very tough to handle very thin substrate. Okay. So what is basically here, why what is this signal mode is generated or resonant mode is generated? Basically we have a perfect confinement of acoustic signal within this piezoelectric mode layer. What do you mean by this confinement of acoustic signal? Means once we have a excitation of any electrical signal through top and bottom electrode, what will happen here? This acoustic wave generated, and there will be mechanism of travel between the top electrode and bottom electrode. If it is not done, then what will happen? Our resonant mode will be disappear. So why it is resonant mode is generated? Because top side we have a air and bottom side also we have a air. So here air will be created as a perfect reflector for my acoustic signal. So what will happen once this acoustic signal comes to top electrode, top side we have air, so it will reflect back to bottom side. And once it will come to bottom side, again bottom side also we have a air, so it will be reflected back. So our acoustic signal will be travel back and forth in between the piezoelectric substrate. Okay.
So how to define the thickness of this material?
This thickness is depending on the substrate, sir, because these ready-made substrates are available, quartz substrates. Okay, so that's why we have a limitation there. We can't go beyond a particular frequency. So now we will come to new devices where we have a control in our hands. Whatever frequency you want, we can develop.
Means that one is the standard.
Yeah, that is the standard because for example you need 1 megahertz resonator for sensing purpose or whatever purpose. So you have to select that particular thickness quartz substrate because different size thickness in our not in our control in this QCL, because this is dedicated substrate available. What is in our control? We can deposit this top and bottom electrode, but that will not decide our resonance frequency. But who will decide? This quartz substrate thickness only. Clear? So now we will move to another device, that is the F bar. Yeah, that frequency depends on the confinement of signal. But actually, how this resonant frequency value will be decided? That value is depending on the value of my thickness of the substrate, because Fr is given by V by twice of Tp. So V is the my acoustic velocity of my substrate and T is the thickness of my substrate. But here acoustic velocity is fixed for quartz, because that we can't change. What we can change? We can change thickness of my substrate. Okay, so we can have only in our hand substrate thickness. Here. So now we have another device, thin bulk acoustic resonator. So what we have here we have first silicon substrate, and over which we will deposit a oxide layer, and then we have a bottom electrode, then we have a piezoelectric layer, and then we have a top electrode. Okay, so now all these three layers we can deposit with the help of photolithography and patterning. So in this case, this maintaining or thickness is in our hand. What kind of thickness we want, we can control with the help of deposition process for piezoelectric layer. But again, for this FR also we required a confinement of acoustic signal within the piezoelectric layer. So how we can confine our acoustic signal into this piezoelectric layer? So we have different kind of structure for this acoustic device. So what we have, first we have a air cavity type structure. So what we have here, we have a silicon substrate. Then we will fabricate a first bottom electrode over the silicon substrate. Then we deposit and pattern piezoelectric layer, and then we deposit and pattern the top electrode. And after that, we will make a cavity backside of the silicon wafer. So what we have, top side we have air, and also backside we also have a air cavity. So what will happen once we excite this acoustic resonator, then stress will generate, and due to this stress, this resonator will be vibrating on a particular frequency, and that frequency is depending on the thickness of my piezoelectric layer, and that I can control with the help of my deposition process. So what will happen, once this acoustic signal travel back and forth, so top side it will be reflected because of air, and also bottom side I have a air cavity. So it is easily travel between back and forth between top electrode and bottom electrode. Once you can done this, you can design your resonator. Now you have a resonator in your hand. What can type of work you want to do? You can perform any kind of work. For example, you want to use it for communication purpose, you can design filter, detector, whatever you want. And if you want to use it for sensor, then you have to use one sensing level top of the top electrode, and you can use for sensing purpose of mirrors. In second structure, what we have, instead of this air cavity, what we can do, we can use a reflector. So what is basically reflector? Reflector is the combination of two layers that has a very high acoustic impedance ratio. Means here I have an oxide and tungsten. So both these layers have a different acoustic impedance. So that acoustic impedance ratio, it is very high, then we require a less number of mirrors. So here basically we use 1 mirror, 2 mirror and 3 mirror. So here we use 3 mirror to confine our acoustic signal. How I say confine? Because once this acoustic signal excited by any our electrical signal, then what will happen? It will travel back and forth between my ZNO layers. So once it will come to this bottom electrode, that is my MUV, then what will happen? Due to this mirror, it will reflected back to my ZNO layer. So this reflector mirror will be work as a mirror for my acoustic signal. So once it will comes to bottom electrode, then it will comes to mirror, then due to this mirror it will reflect back to my ZNO layer. So it will be travel back and forth between my ZNO layer. Clear? So here also we can confine our acoustic signal with the help of mirror as compared to cavity. But top side same we have a air. Okay. Then next structure we have a this what we can say membrane over a air gap. So here we use bulk micromachining and here we are using surface micromachining. Do you know what is the difference between bulk micromachining and surface micromachining? In bulk micromachining, we have to make a cavity below the silicon with the help of bulk micromachining. Bulk micromachining means we are using PIMA process or we are using DRI process, deep reactive ion etching process to entirely remove the silicon backside of the wafer. And in this surface micromachining, what we have basically first we have a silicon substrate and then we will deposit a one sacrificial layer. What do we mean by sacrificial layer? Later we can remove that layer. So we will deposit a sacrificial layer and top of the sacrificial layer we will deposit my bottom electrode, then piezoelectric layer and then top electrode. Okay. And once we deposit, we can remove this sacrificial layer by the etchant of that particular layer. Here. So here again this air will be created as my reflector for the bottom electrode and top side again we have already air. So this three structure we are used for confinement of acoustic signal. Understand? And this is my equivalent circuit. So this acoustic resonator is somewhat to our crystal oscillator. What do we have in crystal oscillator? We have a two type of resonant mode. One is the series resonant and another one is the parallel resonant. So here also we have a series and parallel resonant mode generated with the help of this equivalent circuit. Understood? So if you have doubt, any kind of, because if you have a good understanding about this device, we can easily throughout the day because we have to roaming around this device only. So if you have good understanding, we have a fruitful discussion. So if you have any doubt regarding this, how this acoustic resonator is working, you can ask any kind of whatever it is going in your mind, you can ask anything you want. Whatever it may be, very small doubt, you can ask. I am happy to answer. Anything, it may be material, it may be thickness, it may be complementation, whatever in your mind. What you are expecting today from my side? Can you give me answer? With the help of you are seeing my title, then what you are expecting from the day from me, so that I can deliver to you. So it will be clear vision today for me, so that I can deliver that thing. At least you can give what you expect, what you see in this, because you have some excitation today. Yeah, today is this lecture, so at least we will see we want this in this lecture. What do you want exactly from this? Any questions? What do you want? That you can give an answer at least. Ask a question. What you want? It is your choice. Anything, maybe. Nothing. Expectation. Okay. Later we will come to this question. Once you have to have a good bonding with me. So now we have a how these resonant modes are generated. So for that basically we have a different type of wave mode. So we have basically longitudinal mode, relay mode and transverse or share mode. So So, what is the motivation towards my today's session? So, basically, whatever the device are using or we are learning today for the day, that can be, you can have a different type of structure. Means you can think beyond that also. Means first we have a cavity based F bar, then we have a membrane over a air gap based F bar, that is throw. First one is throw. We have a bulk micro machine. Second one we can fabricate with the help of surface micro machine. Then third one we have a SMR based F bar, that is based on the reflector layer. And third structure we have a polymer based. Means instead of mirror, we can use a polymer that has a acoustic impedance near to air. You can think about which polymer can give you a acoustic impedance similar to air. So we can, instead of mirror, we can utilize that polymer layer to reflect our signal. Because anyhow, what is my goal towards this device? Anyhow, I have to confine my acoustic signal. And how I can confine my acoustic signal? With the help of creating a reflector for the bottom electrode and top electrode. So top electrode I need not to worry about, because top side I have a air, I am worried about bottom side. So for bottom side, how I can achieve a confinement? We have a three method. Either we have to use air cavity to confinement of acoustic signal. Either I can use my mirror to reflect my signal back to my piezoelectric layer, or either I can use polymer as a reflector to reflect back my signal to piezoelectric layer. Because anyhow I have to move or my acoustic signal between the piezoelectric layer only. Otherwise what will happen? Your piezoelectric signal will be penetrate into your silicon substrate and your acoustic signal will be vanished. There is no more generation of acoustic signals. Clear? Then we have different kind of application. We can use any application, because why this device is important? Because it will help you to think about your PhD also. Clear? You can use this device if you are interested in communication, then you can use it for filter design, reflector design, or frequency regulator. Then you can use it for physical sensing, means you can use for UV light sensing, temperature sensing, pressure, humidity, anything you can sense with the help of physical sensing. Then you can use same device for chemical sensing like organic gas, toxic ion or explosive, you can detect with the help of this device. Then you can use it for biological sensing, antigen and protein you can detect. But also you can use for detection of chemical warfare agent. So what we need to change here, we need to, whatever you want to sense from this device, you have to think about sensing there. Because we have a device. Now it's in your hand what you want to utilize, for what purpose you want to utilize this device. Either you can use for sensing, like physical sensing, then what type of physical sensing you require, you have to think about that particular sensing layer. You have to optimize that sensing layer with the help of process. So many processes are there. We have a sputtering method, we have a hydrothermal method. So you can use any method to optimize. So you have to focus only on your optimization of your sensing layer for that particular sensor. Okay. So first we have a application of this acoustic regulator to design a filter. So what we have basically, we have a different, first we have to optimize my device, and I can use this device structure either in the ladder type, P type or L type. Clear? And what we have here, we have two types of anti-resonant frequency. So anti-resonant frequency of the series regulator is equal to resonant frequency of parallel resonator. So that we can design a particular type of my filter. So it depending on your combination of your, how you have to utilize this duplexer, how you have to utilize this resonator, and how you have to connect. According to that, you have to tune your pass band response. Clear? And this is the image of fabricability. Whatever we have arranged here in the shape of L shape, similar we have to fabricate same thing over a silicon substrate. Clear? So we will see how we have to fabricate this thing also. Understand? So we can utilize this device for the purpose of filter also. for frequency tuning also. Means we can use this device with MEMS capacitor. Clear? So what we have here basically, I have my this acoustic device, and here I can use a one air gap capacitor. So what I have here basically, I have my this acoustic generator, and I have here my capacitor. So with the help of this capacitor, I can control my frequency of this generator also. Clear? Because it will increase or decrease the thickness. Because here you have a diagram, so you can increase or decrease thickness. So you can tuning your frequency with the help of combination of your switch with resonator. Clear? So we have another application we can use for tuning of your signal. Then we have a different type of material. How we have to use this different material to for different applications. That different material. So for example, you want to design a particular resonator, and you have to think about which type of material you will be used. So for that we have a different property. We have to see acoustic impedance and density. So what we want basically, if we want to high resonant frequency resonator. So what should be your material quality? Its density will be as low as possible, because this density will increase your or increase or decrease your frequency. Because what we have, our frequency is V by 2 pp. So if you increase your thickness, your resonance frequency will be decreased. So how you increase or decrease? Because if this density will be mass loading to your device. So you have to select that material that has a very low density, but what should be very high acoustic impedance, so that will be perfect confinement of acoustic signal. We have to take care about the confinement of acoustic signal also. So we have to select according to that. So it will be so like that. Generally we use gold as a substrate, but if we are not thinking about my filter design, then here we have a aluminum. Aluminum has a low density plus also have a low acoustic impedance. So we have to think. So like that CMP is very good in the form of confinement of acoustic signal, but it has a also a very, so it will be looking good. CMP is seen. So CMP we have a high acoustic impedance as well as a low density. So if we are thinking about filter designing high frequency, so it will help us to design a high frequency, because it will create a low mass density to my resonator. Then we can use this device for liquid sensing and mass sensing. So this is the my equivalent circuit. So what will happen if I have a liquid sensing anything? Then there is another structure will be created, that is L2 and R2 added into my is Motional R. So this L2 and R2 changing according to your liquid loading to your sensor. And if you have a mass loading, then this L3 will be added into your equivalent resistance, equivalent structure, and this L3 will be changing according to mass loading. So that is L3 is used for your sensing purpose, physical sensing, means gas sensing, pressure sensing, UV sensing. In that case, this L3 will be varying. But in liquid sensing, this L2 and R2 will both will be varying. Clear? Then we can use this for UV sensing. So what can happen into the UV sensing? We have this acoustic velocity formula varying by V naught. So this acoustic velocity is depending on your conductivity of your radioner layer. So this conductivity of your radioner layer will be vary according to you have a UV rays falling over your piezoelectric layer. Because once your UV will fall, then there is a generation of electron and hole, and due to this generation of electron and hole, there is a increase of your conductivity, and due to this your velocity will be changed, and according to that your change in frequency will be changed. So what we are basically have an output in this UV sensor, we have a change in the frequency only. Like that you have a metal MIM sensor or film transistor. So what we have there as a output we have a change in the current according to change in the quantity of that particular sensing. So here we have a, instead of change in current, here we have a change in frequency. So that's why we have correlated this change in frequency with particular UV exposure. Clear? So we will measure change in frequency with for different intensity of
Sir,
Yes.
can be used for medical equipments also?
We will come to that one also. Everywhere, whatever you think you can do with the help of this device. Clear? Now I can come how we have to go for packaging of device. Because see, if you fabricate this device, but to measure the performance of this device, you require a DNA, and you can't purchase DNA because its cost is around 1 crore. So how you have to measure the response? So for that, we can design an interfacing circuit for my device. So what you have in this interfacing circuit? You have one F bar and another F bar with sensing layer. For example, we want to design it for a particular sensing purpose. So what we have one device without sensing layer and another device with a sensing layer. Clear? So then we have this sensing oscillator and reference oscillator, and then we have a mixer. So what this mixer will give? Mixer will give the delay of both of the resonators. Clear? So once we have this frequency, for example 2.4 GHz and this frequency 2.45 GHz. So this will give me approximate 0.3 MHz frequency as a output. So that is the constant. Clear? And then after that I have a low pass filter. So for that I can convert my signal into a variable form, that is in the form of voltage. And I can easily interpret this voltage in the form of whatever the your level of your gas or UV intensity, you can measure in the form of voltage. Clear? Like you measure your current and output in the case of transistor in the form of current, then we can measure our output in the form of voltage. Clear? So what will happen once, for example, you have a exposure of any carbon monoxide gas over the sensor, then what will happen? Nothing will happen to this device because there is no sensing there. But in this device, what you have a sensing layer. So there is a absorption of that gas over to the sensing layer, and due to this absorption, what will happen? Mass loading happen to my resonator, and due to this mass loading, what will happen? My resonant frequency get down, shifted down, and that's why we have a increased delay, and that delay we can measure with the help of mixer, and that delay we can read in the form of voltage. So we can find out how much sensing we have in the what kind of level of my gas, maybe PTT, PTB or PTM, whatever the level, we can easily measure this sensing. Understood? So for example, if you want to biological or any medical, in that case you have to decide about that sensing level. What kind of medical sensor you want. So for that, according to that, you have to work on that particular sensing layer. For example, you want to use for DNA detection. So for that, what kind of sensing layer you require for DNA detection, you have to design your regulator with that particular sensing layer. Okay, but this interfacing circuit will be common for what? Clear? So once we have this interfacing circuit, we will not require a DNA, because what is here? Output is in the form of voltage. Otherwise, what is the output for this device alone? This device alone output is in the form of frequency, and that is very high. That is in the gigahertz. So for measuring gigahertz, we require a DNA. So we can overcome this problem with the help of interfacing circuit. Why these MEMS devices are so not so much popular in India? Because we do not have a fab lab. Fab lab for what? IC technology. Because this interfacing circuit is depending on what? Your VLSI lab. And we have only one fab lab. Where it is? Can you guess? Anyone? SCL Chandigarh. IC Bangalore, we have a MEMS lab, not a VLSI lab. Okay, so there we have fab lab. That is earlier we have 180 nanometer technology in SCL Chandigarh. Now we have 90 nanometer. But earlier it was open to all, but now it is acquired by ISRO. Clear? So because of lacking of this fab lab in India, these MEMS devices are not so much popular. Clear? Because now you have to sell your devices, or how you have to go for R&D. For that you require an interfacing circuit. Clear? Because if we are doing something want from you, so they will provide you some particular specification. How you can achieve that particular specification without the interfacing circuit? Because they want to handle device. They do not interest. See, for example, 10 there is late mark. But coming 3 to 5 years, we have a ordinary capillaries in the process in Gujarat, Assam, everywhere. 2 to 3 capillaries are in India. So again, this popularity of banks will come into a role because these sensors are utilized everywhere: mobile, automation, automated industry, vehicle, everywhere you are using this. Here. So that's why still these devices are not popular. It is only in the academic institute or R&D level only. Because whatever the ISRO want, DRDO want, they have to import the devices from China or Taiwan, whatever way they want. They are not interested from India. Because we are fabricating devices but we do not have an interfacing circuit. So we can't deliver whatever they want. Clear? Then we have a different method of optimization because see, this device looking by is very simple, but understanding how it will be optimal because so many problems there is a generation of higher harmonic mode, increase mode for your resonance. So how can you avoid? So there is so many you can changing your structure of your top electrode, this is like that, and with the help of that you can improve your acoustic because see whatever here we have so many spurious modes are there. So because see if we want to design filter, we want this response spurious field or higher harmonic field. So for that purpose we need to optimize. So how can you tell me how can you optimize this device? You have to think either you have to enter into a web lab and do so many times fabrication, but it will increase your cost. Then what will you do? Yeah. Next option you have is simulation. Clear? So you can reduce your cost by doing lot of simulation. So simulation will also help you to understand more about the device also. So with the help of simulation, you can optimize your device. But nowadays we have an AI also. So with the help of that we can also overcome the time that is spent in your simulation. Because anyhow you have to go for simulation, but you can reduce your simulation time. Clear? So we will decide some objective for our today's work, what we are going to do. So first we have to design and simulate a part to study the confinement of acoustic signal for detailed structure and compare the performance parameter using 2D. So first we will discuss how you have to reduce your time by simulating your 2D devices because if you go for 3D you require a huge time. So how you can optimize your device by designing a 2D device, and then we will move to once our device is optimized we can go to 3D simulation. So we will see how we have to use this simulation process to optimize the device. Then we have to use 3D simulation to remove, because see we can't remove this spurious mode and high harmonic mode with the help of our 2D device simulation. So for that purpose, because this 3D device exact response will give you whatever your fabricated device. So for that we can see how we have to do the 3D simulation for our acoustic resonator. Then how to design the mask layout for purpose optimized structure. Because once you design or optimize your device, then next goal is what? You have to fabricate it. So for fabrication, how can you do? For that you require a mask. What do you mean by mask? Because we fabricate your device with the help of what? MEMS technology. And MEMS technology, what you require? You require a mask. Why you require mask? For patterning your structure. How can you pattern your structure? With the help of photolithography, we can pattern our structure. So for that purpose, we will see about the fabrication process for that particular device. And then finally, we will see how we have to use that particular device for your sensor or filter technology. Clear? So we will go through all these research objectives. You can align with your further PhD or whatever you want to follow. So you can see how, if you are thinking about, I am not saying that you have to use this device. You can think about same MEMS device that is very research part. Clear? That will help you to think about your research part other than your academic part. Clear? Because you will no more survive without the help of research. Because institute what want? So first, so first selection of substrate. So we do not have so many options for selection of substrate. We have a silicon substrate. Clear? Then we have a electrode selection. So it depending on what kind of application you want, based on that you have to think about your electrode. So what we expect in our electrode, it should be low density to minimize the mass loading to my resonator. Then high acoustic impedance to confine my acoustic signal gradually. Then high conductivity to minimize the series resistance in the transmission of excited signal. So I need to think, once I am thinking about my electrode material, I have to think three parameters. It should be low density, it should be high acoustic impedance, and it should be high conductivity. Clear? So we have different material available to us, aluminum, gold, platinum, tungsten, and titanium. So we can, with material we can use for our device electrode purpose. So it depends on the application to the application. Then we have piezoelectric layer. So in piezoelectric layer, nowadays so many piezoelectric materials are available. ZNO, aluminum nitride, BJT, some what we can say ferroelectric material nowadays available for the purpose of tuning of your resonator. So different kind of material and the piezoelectric material we can use. So today we will discuss about ZNO, how you have to use ZNO to design your resonator. So once you think about this, what is in this device? Only I have one piezoelectric layer and one electrode. And once I have decided about material, then I am entering into my simulation part. Understood? So what is the criteria for material selection? First I will select my substrate, then I will select my electrode combination, what type of electrode I can use, and then I have to choose particular my piezoelectric layer. So what I selected, then I have to go for simulation of F bar. So I will go for 2D and 3D simulation. So what I expect from my 2D and 3D simulation, then for how I will achieve that. So for that purpose we have different software available, COMSOL and CoVentorware available for optimize your device. Then you have to use this 1D modeling, means equivalent circuit. So you have to extract the parameter of your equivalent circuit. So you have to find the change in your frequency, then what will be the change in your equivalent circuit. So you have to find out the change in the parameter for your equivalent circuit. Then we have to see how we have to fabricate this F bar with the help of designing the mask, and then we will do the see how we have to characterize of this. Because once you have fabrication, you must have idea what type of characterization you require to validate your result. So we will see that thing. So how much time will we take? 10 minutes. After 10 minutes. Okay, good. So we will understand about different material and we will close this. Then we will start simulation part. Okay. So what we have basically, we have a different material, piezoelectric material as well as our electrode material. So what we have a ZNO. This is the ZNO density, Z modulus, and acoustic velocity. So if I am thinking about my piezoelectric layer, what I am looking for my frequency. So how I decide my frequency? I have two parameters. What these two parameters are? Chalk is required. See, I have this resonant frequency that is depending on my B divided by twice of dB. So this B is my fixed for any piezoelectric material. For example, ZNO. What is my acoustic velocity? 6330. If I will select aluminum nitride, that is 10,127. So if I take high frequency resonator, which material I will choose as electric material? Aluminum nitride, because it has a then you have to decide how you have to choose particular type of. Yeah, because what frequency you are targeting. For example, you are designing a 5G filter or 6G filter. So for that, how will you achieve that frequency and that frequency band? That is very important. So how will you achieve that? With the help of that parameter, that particular equilibrium have. Clear? So I have this density and as well as my acoustic capacity. Based on that, I can decide about my frequency. If I am looking for very high frequency, then I am going for elemental diameter. And if I am looking for simple my sensor, then I can go for ZLC. But still see, if you select means you have to optimize. This is not very easy to deposit this because see in India more than 1,000-2,000 people completed PhD only in ZNO optimization. You see paper, once you ZNO optimization, you will see you have a 1,000-2,000 of PhD only in ZNO characterization, ZNO optimization. So it's see very thin film ZNO deposition is very easy, but here we required a bulk ZNO layer. Bulk means we required it in micron, 1.5 to micron.
I think sir, cost also matter.
Cost it doesn't matter man, because see whatever thickness we require, time is matter. Clear? Time will, once you start your process, it will hardly there is a 10 to 15 minute difference. Initial time it will require to get vacuum and everything that required. So it required for all setup. Clear? So
For the higher frequency, then what we have to do for higher frequency? So if some of the gigahertz.
So for that we have a preserving material, aerodynamic material, so many smart material nowadays. So you can optimize that material also.
These all works are only up to kilohertz.
No, gigahertz. Yeah. See, if we calculate this acoustic velocity, for example, if I will select 1 micron thickness of my element diagram. So this 10,127 by 2, you will get 5 gigahertz. For example, single you have to use 6 dB. Then if you use for example this thickness equal to 1.5. So this 6 dB divided by 3. So you will get your frequency according to that. So it depending on your thickness of your equilibrium.
That will also depend upon the DP.
Yeah, DP is your thickness. DP is thickness.
That is inverse.
Because it is velocity is fixed for that particular material. You can't control that. What you can control here? Thickness. And thickness in your hand because you are going to deposit that particular layer. Yes, it is in your hand. How you have to deposit. Because we see first QCM, quartz crystal micrographs. So in that we do not have a controllable heat because our substrate size is fixed.
If the technology is also increasing the thickness, then the frequency is also affected.
Yeah.
Okay, so if you do, what is the limitation for the thickness?
There is no limitation, sir. Because see, it depending on what, because see, you can't go beyond a particular thickness. For example, you can't go beyond a particular.
That's what
If you want to go for example, if you want to deposit 0.2 micron thickness, that is 200 nanometer. You can't able to manage your resonance because it requires bulk. Because your signal will be travel back and forth into your electric phase.
this kind of minimum and maximum limit I think
Yeah.
to decide it to what extent.
See, if we want to go for bulk acoustic, at least we have a 0.7 micron